Alright, this example focuses on an amusement park that has a Ferris wheel 200 feet in diameter. Let's go ahead and draw a graph of a wheel to give us an idea of what's going on. So we have this Ferris wheel, and I guess the diameter is going to be, so this height of the wheel is 200 feet. And just carrying on here, the wheel rotates at a constant rate and completes a rotation every 40 minutes. So it's a pretty big wheel and it takes a while to get all the way around it. If we let h of t represent the height in feet of a Ferris wheel passenger t minutes after boarding the wheel at ground level, let's sketch a graph of that height function, y equals h of t. So to accomplish this, we're going to need a coordinate plane. So let's go ahead and slide the circle over to the left and plop a coordinate plane down so that we can draw a graph of the height of a passenger who's going around this Ferris wheel. Alright, now we can draw a graph of the height of the Ferris wheel passenger, and to get started we should aim for the easier pieces of information if we can. As we were told, the Ferris wheel passenger boards the wheel down here at ground level, and then, at least as I've got it drawn, the wheel will rotate in this counterclockwise direction. It doesn't really matter which way we imagine that the wheel will rotate. If we all we're interested in is our heights. Let's just sort of arbitrarily assume we'll go counterclockwise. And so since we're starting our rotation around the wheel here at ground level, at time equals 0, our height will be 0 feet. So we can plot that red dot there at 0, 0 on our graph to represent that at the time 0, our height will be 0. And then what we can do is rotate ourselves around the wheel. An easy type of rotation will be a full revolution, right? If we get all the way around the wheel, it's pretty obvious where we'll land, right exactly where we were before. So our height will be 0 again, and we're told that it takes 40 minutes to rotate all the way around the wheel. So 40 minutes after our first red dot, we'll have another red dot at the height of 0. And 40 minutes later, we'd have another red dot at the height of 0, suggesting that every 40 minutes, we complete a whole trip around the wheel and are back at the ground level again. All right, another pretty easy set of height to determine is the height at the top of the wheel, right? So if we rotate halfway around the wheel, will be up here in kind of maximum height position. We'll be up at the very top of the wheel, and we're told that the wheel is a diameter of 200 feet, so that we'll know we'll be up there at the height of 200 feet. And since the rotation is constant, always rotating at the same rate, we can divide a full revolution's 40 minutes in half. 20 minutes it'll take to get halfway up to the top of the wheel, halfway around the wheel, which would take us to the top. So after 20 minutes, we can expect that we'll be up at the top of the wheel, and then maybe we can just go in 20-minute intervals to kind of see what'll happen when we go around the circle. So we start here at the bottom. After 20 minutes, we're at the top. We just plotted that point there. After 20 minutes, we'll be at the bottom. That's the 40 minutes where it's 0. After 20 more minutes, we'll be at the top again. So after 60 minutes, we'll be at the top again. And then 20 more 80 minutes, we're at the bottom, which we'd already plotted. So every 20 minutes, we go from bottom to top to bottom to top, maximum height to minimum height around the Ferris wheel. Okay, so to get a more accurate graph than we'd get by just connecting these red dots, let's consider how long it will take us to rotate a quarter of the way around the wheel. Right, a quarter of the way around the wheel. Well, that's going to be halfway. It's half of this. Let's clear some of this out. So this was our half trip around the wheel, getting all the way to the top. Took 20 minutes, if we only take half of that trip to get to this midway spot, then we should expect our height to be halfway to the top, or 100 minutes. And since we're rotating at a constant rate and it takes 40 minutes to get all the way around the wheel, this amount of rotation will take 10 minutes. It'll be 10 minutes to the middle, 10 minutes to the top, 10 minutes back to the middle, and 10 minutes back to the bottom. So every 10 minutes we go from minimum to middle to maximum to middle. Okay, so we start at this minimum spot at 0. 10 minutes later we'll be halfway to the top. 10 minutes later we're actually at the top. 10 minutes later we're at the middle again, coming down the wheel right here. 10 minutes later we're at the bottom, and continue that rotation. Every 10 minutes we go from bottom to middle to top, from top to middle to bottom. It's a constant rotational speed. Alright, so now we've got some nice dots that we can connect to get a graph of the height function. Now if we do this naively, if we just connect the dots without thinking much about how the graph should look, we might end up with something like this. Right, and this isn't a crazy interpretation of the situation, but it turns out that it's not accurate. The problem with this sort of interpretation, well, I think there's arguably sort of two ways of looking at why this can't be the correct shape of the graph. One way that this seems problematic is that the behavior, for example, here when we transition in and out of the maximum height. The way that this graph makes it look, it seems that we are kind of going full speed up, climbing at a constant rate, full speed. We reach the maximum height value, and we spontaneously stop and turn around and go back down at the exact same full speed, but downhill instead of uphill. And if you imagine if you're going around a wheel and it did that kind of a Ferris wheel, and it did that to you. You were going full speed up, never slowing down as you reached the peak, and then immediately switched direction and went straight down. It would be extremely jarring and, I promise, an unpleasant Ferris wheel trip. So luckily that's not actually what happens when you go around a Ferris wheel. Another problem with this way of interpreting the data that, our dots, our green and red dots, is that it suggests that, for example, through this, in this region here, between like 0 minutes and 20 minutes, we have a linear function there. This has a constant slope. So it suggests the heights are changing at the exact same rate throughout that entire period of time. But it turns out that's not true. The heights, when you're going around the wheel, are not always changing at the same rate. Our rotational rate is constant. That's what we were told in the question. But our height change, the rate of change of our heights, is not constant. So notice how in like this region of the circle, when our Ferris wheel carriage is traveling through this region, maybe that we could call that the eastern hemisphere sort of area of the graph, of the circle. When you're traveling in there, your travel is almost entirely vertical. We should expect to be going quite quickly in the uphill direction. But then when you compare that with this region over here, on the top of the circle, our vertical travel is very minimal. Our travel is much more horizontal than vertical, so we aren't climbing very quickly there at all. So we need to reconsider how we drew this graph. Let's see how much of this I can erase away without ruining the dots. All right, so let's draw this graph with the sort of specific rate of change in different intervals on the circle in mind. So as I was just showing, in this area here, we expect our heights to be changing quite quickly because we're almost just traveling in a pure vertical direction. So when it comes to drawing our graph in that area, when we're at this around 100 feet area region of height, we should expect our graph to be pretty steep there. But then when we compare that to like this region up at the sort of North Pole, where our vertical travel is not very significant, we should expect the graph to not be very steep, for our heights to not be changing very much up there when we're near the 200-foot level, right? When we're up at the peak of our graph. So we should expect the graph to, the heights to change quickly on the left and right regions of our circle, the left and right poles, if I could use that phrase. And we should expect our heights not to change very much on the peaks and valleys, on the maximal and minimal portions of the graph. So we have this kind of expectation on the shape of the graph. And it turns out that the correct shape of this graph is going to kind of mimic these little green and orange ticks I've drawn. It turns out that our heights will kind of, whoa, that's a bit too thick, I believe. So let's go to a smaller color thickness. Our heights will kind of increase in this way as we go around our circle. We'll get a nice curvy, wavy shape. And notice I'm drawing each quarter wave kind of corresponding to the quarter circle that we were going around. So it turns out when we plot our heights as we go around a circle like this, we get a nice curvy wavy shape. And notice that the graph is periodic. It repeats the same shape over and over again because we're going around a circle. So we keep experiencing the same height changes in each revolution around the circle. Every trip around the Ferris wheel, you do the same thing. You start at the bottom, get to the middle, get to the top, get to the middle again, and down to the bottom. Every time, same experience, and so we expect a periodic function to come out of it. I've tidied up this graph a little bit, and here's the cleaned up version if we had just used technology to graph it.